Welcome and thanks everyone for having me as part of the Bays and Bayous Symposium. I'm Joann Mossa from UF, and with my co-author Chen, we'll be talking about a retrospective analysis of a dredging and disposal problem area in the Apalachicola River. So the Apalachicola is in the Florida Panhandle. It was dredged for a navigation project aiming to create a navigation channel that was 9 foot deep and 100 foot wide. 30 million cubic meters was dredged during this project, which began 60 years ago and ended roughly 20 years ago. Dredge spoil was placed on the floodplain and channel margins. There was very little guidance for river dredging and disposal 60 years ago, and we know a lot more about the ecological impacts during dredging, but not so much about what happens with the spoil that's placed on the floodplain and bars in the decades that follow. Sediment can create many problems, and so this study is doing a retrospective geomorphic analysis of what went wrong to inform future dredging on rivers elsewhere. So we're going to focus on disposal sites downstream of Chipola Cutoff. Chipola Cutoff is near river mile 41 to 42. It's a distributary natural feature that diverts roughly 30% of the flow down the lower Chipola. There are several eroding dredge spoil mounds shown by the red arrows along the Apalachicola below this cutoff. Our focus is on Site 40 near River Mile 36, which was a problem for the Corps. So besides the hydrographic data that was collected along the entire river from 1960 and 2010, we also have some topographic and hydrographic data from 1981 and 1988. The history of Site 40 actually begins with artificial cutoffs. There were two of them made between river mile 35 and 37. One of them became Site 40 when the cutoff was filled with dredge sediment, and the same is true for Site 38 downstream. The pre and post cutoff situation can be seen by how the sinuosity of the river has changed and how these two artificial cutoffs became disposal sites. And then by 2017, the upstream bars were growing because they were also disposal sites. So the riverbed becomes shallower downstream of Chipola Cutoff, shown here between river mile 41 and 42. There's a big shallow area there, and there's a second shallow area here between river mile 37 and 36. So because the river was shallow in these locations, these two areas became dredging hotspots. About 25% of the river dredging occurred in these 7 miles. And most of it was during the 90s and secondarily during the 1980s, as shown. So the graph on the bottom right shows disposal volume since 1980. There was a lot of disposal between 1960 and 1979, but we don't have that data available. The upstream bar, Site 43, had the most disposal in the 90s, and the site across the river had most disposal in the 1980s because Site 40 was mostly full by 1990. Here you can see the 3D evolution of the bend and bed. First the original channel, then the channel becomes a disposal site when the river is shortened. The elevation and size of the disposal site continues to grow through 1988. But after that, it begins to erode at the channel margin, particularly on the downstream end. Here we have graphs showing, or maps showing the elevations of the riverbed and the adjacent disposal site. And then the second row is change maps. So at the top, elevations start growing with the mound getting larger from disposal and then begin to shrink from erosion with some of the sediment depositing in the channel. The lower graphics show change with the green representing addition of sediment, red indicating removal, and we can see a lot of erosion occurring at the margins of the mound, and that sediment is causing the river to fill. So here we have this magenta area, and we're looking at change in this magenta area, which is what we have those 4 periods, what the Corps surveyed. And in there we have more than 600,000 cubic meters disposed at this site. By 2007, about a third of that part of the disposal site eroded back into the river. And so this is 2020, probably much more has eroded since. So there are spatial variations in erosion patterns. On the upstream end of this disposal site, most of the erosion is occurring laterally. So we have as much as 50 meters or more of erosion from 1981 to 2007. On the downstream end, we have a combination of erosion from the riverside and also from overtopping from floods. The eroding mound has altered river form. The channel has become a lot wider and shallower, and changing its width-depth ratio, and the depths and channel elevation show filling with sediment. Here we see a box plot that shows the median and various percentiles of approximately 20 cross-sections near the disposal site. The channel has generally become wider and shallower over time, shown by these changing width-depth ratios and bed elevations that show the lowest point, or thalweg, is about 1.5 meters higher due to filling with sediment. Despite a lot of dredging, waterborne commerce decreased along the river. This specific site and many others continue to erode, and in this location, upstream disposal sites still feed sediment to this reach. This site is on the outer bend of a meander where the depths and current velocities tend to be the greatest, and this steep slope created by erosion continues to provide sediment to the river by mass wasting and flood flows. The Corps has had a specific program to look at dredging for the past 20 years, more so focused on the coastal environment. They have made many advances in engineering and geomorphology since the Corps first dredged this river. But this surveying or monitoring data is essential for better understanding the dredging problems here and elsewhere. So I advocate more retrospective work to evaluate the fate of disposal site sediments and how they impact rivers here and elsewhere. Our take-home message is that some locations are just not well suited for dredging at all, particularly downstream of a distributary. It's very difficult to create those expected channel depths. Disposal can also be problematic in a cutoff zone. The river is readjusting, regaining sinuosity. It's going to erode mounds through that process of increased lateral migration. Outside of a meander bend is generally worse than an inner bend for creating or developing a disposal site. And sites of excessive size will erode for decades, particularly if there's no vegetative buffer. Disposal upstream of a problem area will also feed more sediment to the problem area, so that is also not a good practice. So I advocate, again, more retrospective analysis of disposal sites in more rivers, because this is just one sample location on one section of one river. Another potential application is in rivers that are mined for sand and gravel. And this type of framework can be used to make decisions about where to and where not to place extra materials near rivers. Extra thanks are due to the US EPA Gulf of Mexico program for funding this research, and then also collaborators in the past, including Apalachicola River Keeper and Florida Fish and Wildlife Conservation Commission, have supported work on the Apalachicola River. Thank you.